In this problem, a projectile is fired with an initial speed of 400 meters per second and an angle of elevation of 60 degrees. Part A, find the range of the projectile. Okay, so in these problems, you're allowed to use the projectile motion vector valued function that I gave you in the notes for this section. So if you recall, R of t, let me see if I can recall it. I believe the first component is V naught cosine theta times t. And then just, if you want to write it in ij form, times I. The second component, I mentioned the h, even though in these problems you can assume h is 0. H plus V naught sine theta. Okay, I'll put that guy in parentheses, times t. And then generically minus 1/2 the gravitational constant, t squared. That whole thing times j. One thing we might have not talked about enough would be, okay, if you're in English units, what's g? 32. Acceleration due to gravity is 32 in English units. What is it in metric? 9.8, right? Now, I just assumed you guys knew that because it comes up in Calc 2 a lot, right? But I should have probably mentioned it as well the other day. So how do I know we're going to use 9.8 here? Meters. Automatically standard, then we're in meters per second. That means gravity is 9.8. So let's fill this in using what we know. We know theta is equal to 60 degrees. We know V naught, that we call V naught the initial speed, right? Initial velocity. And we know g is 9.8. So let's fill this thing in as best we can. R of t is equal to, help me out here, well, 400. Yeah, but what's the cosine of 60? Cosine of 60 is 1/2. So I'll clean that up in the next step. Okay, h is 0, I said you could assume. So we're going to get, 400. What's the sine of 60? Root 3 over 2. And don't forget the t. And then what do we get when we take 1/2 times 9.8? 4.9 t squared j. And just cleaning it up, I guess we get 200 ti plus quantity 200 radical 3t minus 4.9 t squared j. The projectile might look like that, right? The path of the projectile, that is. This is x, this is y. So what do we mean by the range? We mean the horizontal distance. We're not talking like the function range that you learn about in algebra. It's the horizontal distance, right? Which is controlled by the I component of R of t, right? But I think we're going to have to make use of the j component as well, aren't we? So what do we know about, so we want to find whatever this distance is. But where can we begin? What do we know about the height right here where the projectile lands? Yeah, we're going to make this as simple as possible. The land is flat, the height is 0. Okay, we take off from a height of 0, we land at 0. So what does that mean? What can I do with the fact that the height of the projectile when it lands at the end of the range is 0? What can I do with that 0 value? It's a height value, so what do I have to set it equal to? What do you think? Yeah, the y component. Yeah. So the height here is 0. So you could say y of t, which stands for the j component of r of t, right? You could say that value is 0 there. So we're still going to make use of the second component then. So that would be the 200 root 3 times t minus 4.9 t squared equals 0. Everybody buy that? Now let me show you a cool trick here. We know that t equals 0 is the solution to this equation, right? Do we care about t equals 0? No. So how about, since we know t is not equal to 0, in that case, aren't we allowed to divide as long as we know we're dividing by a variable that's not 0? Or an unknown. It's not really a variable. It's an unknown that's not 0. Well, we can delete that guy, right? And then the t squared becomes just 4.9t, and then 0 divided by t is 0. And we get a slightly simpler equation, right? So can we solve for t then? I think we can. What do we get if we solve for t? Well, as an exact answer, I think we're going to get, the negatives will cancel. We'll get 200 root 3 over 4.9. And then I think we can use this then to get that range, to get that horizontal distance. So where do I put that? I put it in the I component, don't I? So no derivatives necessary here. So my range, let me say it this way, my range is going to equal 200 times t, right? But that t is just this value, 200 radical 3 divided by 4.9. And I'll let you guys do that calculation. What will the units be in? What units of distance? Meters. So you can run that through your calculator. For part B, how would you find the maximum height of the projectile? Well, not quite. Because, okay, we do have to use a derivative for this one, remember. So the maximum, if you think about it, at the maximum height, the j component's velocity will be 0. The velocity of just the j component, think about it. If I were to throw this pin, which would be a bad idea because it's not really a pin, it's a stylus and it'll break. But if I threw it at you, not that I would ever do that, but it would hit a maximum height, right? And would start coming down. At that maximum height, the horizontal component's velocity is not 0, but the vertical component's velocity is 0. So we can use that fact to say that if we take, okay, generically we call y of t the vertical component, right? So we can use that fact that we're looking for the maximum height to say that, okay, y prime of t, which is the rate of change of the vertical component with respect to time, if we set that equal to 0, that t value that we find will correspond to the maximum height, won't it? So then what do? You solve for t. So t equals t naught. And then that's not the actual maximum height. How do you find the maximum height? Whatever this value turns out to be, which one do you plug it into? The j value of the original position function, right? So that would be y of t naught would give you the maximum height. Does that help? Okay. So I did one kind of like this in class, so I wanted to save time and just kind of give you the bare bones of how to do it. Now, what would the speed of the projectile be upon impact? Okay, what gives you the speed, first of all? So the magnitude of what? The magnitude of v of t, right? So what's the t value? We already know the t value. Isn't this the t value upon impact? So you could just plug that find the magnitude of v of t first, and then plug in t equals 200 root 3 divided by 4.9. Does that make sense to you? But you have to find, remember what v of t is, it's r prime. So you have to take the derivative of this guy, and then you could either plug in the t value right then after you take the derivative, or take the magnitude and then plug in the particular t value. It doesn't really matter, whatever is easier. And then that will give you the speed upon impact.